1. NASA's SNIFS, Unraveling the Mysteries of the Sun's Chromosphere. 2. NASA's SNIFS mission, Exploring the Sun's Chromosphere. 3. NASA launches sounding rocket from New Mexico, exploring the Sun's chromosphere. 1. NASA's SNIFS, Unraveling the Mysteries of the Sun's Chromosphere. NASA is set to embark on an exciting journey with the launch of the Solar Eruption Integral Field Spectrograph mission, commonly referred to as SNIFS. This innovative mission, scheduled for July, will be propelled into space by a Black Brant 9 sounding rocket. Its primary objective is to investigate the energy dynamics and intricate behaviors of the chromosphere, a particularly complex layer of the Sun's atmosphere. The launch window for the SNIFS mission will open at the White Sands Missile Range in New Mexico on Friday, July 18. The chromosphere is situated between the Sun's visible surface, known as the photosphere, and its outermost layer, the corona. While extensive research has been conducted on the various layers of the Sun's atmosphere, the chromosphere remains shrouded in mystery, with numerous questions still unanswered. "There are still many unknowns," remarked Philip Chamberlain, a research scientist at the University of Colorado Boulder and the principal investigator for the SNIFS mission. This mission is particularly significant as it aims to shed light on the processes occurring within the chromosphere, which is crucial for understanding solar phenomena. The chromosphere is not just a passive layer, it plays a vital role in solar activity, including solar flares and coronal mass ejections, which can have profound effects on space weather and, consequently, on Earth. These solar eruptions are the primary drivers of space weather, creating hazardous conditions that can jeopardize satellites and pose risks to astronauts. The SNIFS mission seeks to unravel how energy is generated and transferred through the chromosphere, ultimately contributing to these massive solar explosions. "To ensure the safety of Earth from space weather, we need to develop accurate models," stated Vicky Hurd, a doctoral graduate from CU Boulder who collaborated with Chamberlain on the SNIFS project. The SNIFS mission is groundbreaking as it represents the first solar ultraviolet integral field spectrograph. This advanced technology merges the capabilities of an imager and a spectrograph. Imagers are adept at capturing photos and videos, allowing for a broad view of light from a large area simultaneously. In contrast, spectrographs analyze light by breaking it down into its various wavelengths, revealing the elements present, their temperatures, and their movements, but only from a single point at a time. By combining these two technologies, SNIFS offers a comprehensive tool for solar research. "It's the best of both worlds," Chamberlain noted. "We are pushing the boundaries of what technology can achieve." Focusing on specific wavelengths, known as spectral lines, the SNIFS mission will provide valuable insights into the chromosphere. These spectral lines include a prominent hydrogen line in the Sun's ultraviolet spectrum, along with lines from silicon and oxygen. The data collected from these wavelengths will help scientists understand how the chromosphere interacts with the upper atmosphere, tracing the movement of solar material and energy. The SNIFS mission will be launched using a sounding rocket, which is an effective platform for conducting space experiments. These rockets not only facilitate scientific research but also offer invaluable hands-on experience for students and early career researchers. Vicky Hurd, along with her colleagues Joseph Wallace and Gabby Gonzalez, expressed their enthusiasm for the project, highlighting the unique opportunity it provides for students to engage with the hardware directly. "You can really try some wild things," Hurd said. "It allows students to get involved in the practical aspects of space science." Chamberlain emphasized the importance of such missions for nurturing the next generation of scientists, who bring fresh ideas and enthusiasm to the field. The entire SNIFS mission is expected to last approximately 15 minutes, with the sounding rocket taking about 90 seconds to reach space, followed by 7 to 8 minutes of experimentation on the chromosphere, and finally 3 to 5 minutes for the return to Earth. The rocket will drift approximately 70 to 80 miles, 112 to 128 kilometers, from the launch pad before landing, necessitating careful planning to ensure a safe landing area. The White Sands Missile Range, with its vast open desert, is an ideal location for this purpose. Hurd, who dedicated 4 years to the project, expressed her excitement for the upcoming launch, stating, "This has been my baby." 2. NASA's SNIFS mission, Exploring the Sun's Chromosphere. Stunning breakthrough on the horizon, NASA is about to launch SNIFS, the Solar Eruption Integral Field Spectrograph mission, to unravel the Sun's most baffling atmospheric layer. But here's where it gets controversial: can a brief, 15-minute rocket flight really transform our understanding of solar storms? And this is the part most people miss: the chromosphere, that thin band of gas sandwiched between the Sun's bright surface, the photosphere, and its fiery outer atmosphere, the corona, still hides many of its secrets. July 18, New Mexico, will mark the opening of SNIFS's launch window at the White Sands Missile Range. Carried aloft by a Black Brant 9 sounding rocket, SNIFS aims to probe how energy and matter flow through the chromosphere, key to predicting the massive solar flares and coronal mass ejections that drive dangerous space weather. Those eruptions can cripple satellites, disrupt communications, and even endanger astronauts on orbit. The chromosphere is our missing link, explains Philip Chamberlain, lead investigator from the University of Colorado Boulder. We've studied the photosphere and corona extensively, but this middle layer still puzzles us. Vicky Hurd, who earned her PhD at CU Boulder and helped develop SNIFS, adds, to protect Earth from solar storms, we need accurate models of how energy converts and moves through that layer. At the heart of SNIFS is the first-ever ultraviolet integral field spectrograph designed for solar research. Traditional imagers capture broad views in photos and videos, while spectrographs dissect light at one point to reveal elemental fingerprints, temperatures, and velocities. SNIFS merges both approaches, delivering a complete, slice-by-slice map of how key ultraviolet wavelengths behave across the chromosphere. Specifically, SNIFS will track three crucial spectral lines. The brightest hydrogen line in the sun's UV spectrum, revealing where and how hydrogen atoms are energized. A silicon line that shows how heavier elements respond to shifting temperatures. An oxygen line that helps trace fast-moving solar material. By combining data from these lines, scientists hope to watch energy ripple upward and trigger those colossal solar explosions. Sounding rockets may sound modest, but they're powerful tools for cutting-edge experiments and training the next generation of space researchers. These missions let students get hands-on with real flight hardware and test wild ideas that larger projects can't accommodate, says Hurd. Chamberlain agrees, noting that early career scientists bring fresh enthusiasm, innovative techniques, and bold questions to the field. The entire SNIFS flight will span about 15 minutes, 90 seconds to reach space, 7 to 8 minutes of chromosphere observations, and 3 to 5 minutes for the rocket to descend and land safely back on the desert floor 70 to 80 miles downrange. White Sands, a vast, uninhabited basin, offers the ideal backdrop for this quick turnaround mission. After 4 years of design, assembly, and testing, Hurd admits, SNIFS has been my baby, I can't wait to see it in action. Thought-provoking questions to ponder. Is investing in short-duration sounding rockets the best way to advance solar physics, or should NASA focus on larger, longer-term observatories? Could SNIFS's innovative design become the blueprint for future space instruments, or will its limitations spark new debates? What if the chromosphere's mysteries don't match our expectations? How would that change our approach to forecasting space weather? Join the conversation below. Do you agree that SNIFS will revolutionize our view of the sun, or is it just another high-risk experiment? Share your thoughts. 3. NASA launches sounding rocket from New Mexico, exploring the sun's chromosphere. Imagine a small rocket taking off from a remote corner of New Mexico, aiming to unlock the secrets of the sun's enigmatic atmosphere. But here's where it gets interesting. This isn't your typical launch from Florida or California. This is a story about NASA's sounding rockets and a mission that could revolutionize our understanding of solar phenomena. Standing at no more than 70 feet tall, sounding rockets are a far cry from the towering giants like SpaceX's Falcon 9, which clocks in at a whopping 230 feet. These smaller rockets serve a crucial purpose. They allow scientists to conduct quick, cost-effective missions to study regions of space that are too low for satellites to reach. It's like sending a scout to explore areas just beyond our reach. While states like Florida, Texas, and California are familiar faces in the world of rocket launches, New Mexico's White Sands Space Harbor steps into the spotlight. On Friday, July 18, a Black Brant 9 rocket will soar into action, embarking on a 15-minute journey to investigate the sun's chromosphere. This mission is part of NASA's ongoing efforts to unravel the mysteries of solar activity and its impact on Earth. The launch is set for 1 p.m. local time, and if skies are clear, residents in the vicinity might catch a glimpse of the rocket's contrail. After reaching space, the rocket will spend about 9 minutes studying the chromosphere, a layer that plays a pivotal role in generating solar flares and coronal mass ejections, phenomena that can affect our planet's technology and communications. What sets this mission apart is the innovative combination of imaging technology and spectroscopy. By capturing both visual data and breaking down light into its component wavelengths, researchers hope to gain unprecedented insights into the chromosphere's behavior. This dual approach is a first for a sounding rocket mission, showcasing the continuous evolution of space exploration techniques. So, why choose New Mexico for this ambitious project? NASA's White Sands Space Harbor offers a unique location for such missions, providing the necessary infrastructure and a vast, open area for safe rocket recovery. This mission is a testament to the fact that groundbreaking science can happen in unexpected places. And this is the part most people miss: sounding rockets aren't just smaller versions of bigger spacecraft. They represent a distinct class of vehicles designed for specific scientific objectives. Their affordability and rapid deployment capabilities make them invaluable tools in the quest for knowledge. But here's a thought-provoking question: could sounding rockets play a larger role in future space exploration? As we push the boundaries of what's possible, might these versatile machines become even more integral to our missions? Share your thoughts in the comments below.